Hello and welcome to ASMR Chemistry. And in our classroom today, we're going to be talking about formal charge. Formal charge has some very good uses, and one of them is predicting the correct structure for molecules, and it can also be used specifically to predict which of the resonance structures is going to contribute to the overall structure the most when you do have resonance. But first we're going to start out with examples that don't involve resonance. And in fact, we might not even get into resonance structures in this video. And if that's the case, I will make a separate video and we can delve into resonance there. Okay, but in terms of formal charge, let's think about what does it mean, okay? And we're going to use an example of HCl, okay? So if we are drawing out Lewis dot structure of HCl, it would look like this, right? Okay. Some people prefer, instead of having a line to represent a pair of electrons, they have it look like this. These two are the same. Okay. So when we're looking at formal charge, this is giving us an idea of how much electron density is associated with a particular atom that goes beyond just making sure it has its octet. We're comparing the number of electrons associated with an atom compared with how many of those electrons that it has as its element. Okay, so I started writing here before I distracted myself. Okay, how we determine formal charge is that, in fact, I'll make this equals 2 because this is gonna be a calculation, all right, where we will take the number of valence electrons. Okay, so this is always, when we're calculating the formal charge, it is for each atom in a molecule. Okay, so we take the number of valence electrons from that particular atom, and then what we are going to do is we are going to subtract out the number of electrons that are in lone pairs, that are not involved in bonding. Okay, so these two would be the electrons that are involved in bonding, and these 3 lone pairs, or in other words, these 6 electrons, these are what we would call non-bonding electrons. Okay, so we're going to take all those non-bonding electrons and subtract them. And we are going to also subtract the number of bonding electrons. But because these are shared, such as these 2 electrons are shared between the hydrogen and the chlorine, we're going to divide that by 2. Okay, so let's do this first for, we'll call it FC, formal charge of hydrogen in our HCl molecule. Okay, number of valence electrons. This is where you will sometimes need the periodic table if you don't know what it is already. Okay, hydrogen, a lot of us might know already that it has one electron, but for completion, we'll take a look at the periodic table. It has that one valence electron, so that will be 1. Okay, then we subtract out the number of non-bonding electrons. Okay, so this is usually, we see that in lone pairs. Hydrogen does not have any lone pairs, so 0. And then we subtract the number of bonding electrons divided by 2. Okay, there are 2 bonding electrons in this bond, right? So we will subtract out 2 divided by 2. This is, of course, 1. 2 for 2 is 1. So we end up with 1 minus 1. Formal charge of hydrogen is 0. Okay. What about the chlorine? Formal charge of chlorine. All right, so we look again at our periodic table, and we see that chlorine is in group 7. It's a halide. Okay, on this periodic table, it's called group 17. But in terms of number of valence electrons, when we're creating our Lewis dot structures, it would be 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 valence electrons in chlorine. Okay, number of non-bonding electrons, 2, 4, 6. We just counted up all those lone pairs. Okay, so we are going to subtract 6. And then we will subtract out the number of bonding electrons. We just saw this in hydrogen. There were 2 of them, and we divide that by 2. So we see that we have 7 minus 6 minus 1 is also 0. Okay, having a formal charge of 0 is a very stable situation. And we will see that for many atoms in molecules, this formal charge is 0, but not always. So that's what's going to help us determine what is the most stable structure. Very helpful. So let's do this with an example of if we were to look at the molecule hydrogen cyanide that has a hydrogen, a carbon, and a nitrogen. Okay? And if we asked ourselves, is the most stable Lewis structure is it H, C, N, or is it H, N, C? Okay, so here's our question. Move this up a little bit. Okay. And we can use formal charges to determine. And that is based on if your formal charge ends up being 0 or negative, that is going to be more stable on the more electronegative atom. If it's 0 or positive, it will be more stable on the more electropositive atom, or in other words, the less electronegative one. So we'll see how that plays out when we inspect these 2 possible structures. Okay. So let's let's calculate for this molecule what is the formal charge of hydrogen. Okay, very similar to what we just did with our HCl example. We have, in fact, I'm going to use a different color, I think, to distinguish. I have my purple fountain pen. Okay. All right, so for our hydrogen here, valence electrons, 1. There aren't any lone pairs, 0, minus 2 over 2, or in other words, 1. So the formal charge on hydrogen is 0. Okay, a little box around that. Okay, what about our carbon here? Okay, so carbon, its valence electrons, let's have a little reminder here. Okay, number of valence electrons for carbon is 1, 2, 3, 4. Okay, so we've got 4. This carbon does not have any lone pairs, so that will be minus 0. Okay, and now, what about the bonding electrons? It's got 2, 4, 6, 8. Okay, so for each of these bonds, that's a pair of electrons. So this carbon is completely bonded, 2, 4, 6, 8. So we're going to subtract 8, but because they're bonding, we divide by 2. Okay, so 4 minus 4 equals 0. Formal charge of carbon is 0 in this molecule. Okay, and now what about this nitrogen? Number of valence electrons on nitrogen. We've got 1, 2, 3, 4, 5. Okay. This nitrogen does have a pair of non-bonding electrons, or in other words, a lone pair. Okay, so we're going to subtract those. And then we are going to subtract out number of bonding electrons divided by 2. 2, 4, 6. And divide that by 2. Okay, so what does this end up being? We have 5 minus 2 minus 3. So that is 0. Okay. So in this molecule, every atom has a formal charge of 0. Now let's look at if the structure were HNC instead. Both of these structures are viable in terms of the number of valence electrons included are all there, and these two atoms have their octets, so that looks good. Hydrogen has 2 electrons, that's good. But formal charge is going to give us some more information. Okay, this hydrogen is identical to this one here. So we already know that its formal charge is 0. How about the nitrogen now, this molecule? Nitrogen has 5 valence electrons. It's got, in terms of non-bonding electrons, we see all the electrons around nitrogen are bonding, so no non-bonding electrons, minus 0. Okay, and now in terms of bonding electrons, 2, 4, 6, 8. We divide that by 2. Okay, so now we have 5 minus 4. That means we have a formal charge of plus 1. Okay, we're finally seeing something different than 0, right? Okay. Now let's look at this carbon. This carbon has number of valence electrons is 4. It's got a lone pair, so we'll subtract that, those 2 electrons, and then we will subtract out number of bonding electrons divided by 2. 2, 4, 6. Divided by 2. So, with carbon, in this case, 4 minus 2 minus 3 is minus 1. Okay, so this is the issue, okay? Nitrogen is more electronegative. Than carbon. The molecule is more stable if the negative charge, when you do have a negative formal charge, it is more stable when it is on the more electronegative atom. In this case, nitrogen being more electronegative than carbon, and it has the positive formal charge, that will not happen. That will not be observed. That does not give the most stable structure. Okay? So, therefore, this is the most stable structure here because we do not have the scenario where the more electronegative atom has the more positive formal charge. Rather, it's got very low, in other words, 0 formal charges. Okay? That isn't to say you can't have a negative formal charge and not have a stable structure. Okay? But separation of charges like this is not as stable as when we minimize them, in this case, where we have 0